Okay, welcome to our last session for the course in nets and vector lattices and functional analysis. So please, Youssef, whenever you want.
Okay, today is the last part, and it will be a small contribution of mine on the topic, and it's about the diagonal transfer. So I will start by recalling the standard diagonal argument or principle, and say a few words about it. Then we have an extension for nets. At first, I will start by the countable case. And then the general case. And finally, I will mention some applications. Okay. Well, the diagonal argument, it's called argument because it is really an argument, is a method of work. So it is used for the first time by Cantor. So it's called also Cantor diagonal argument or process or method to show that there is an uncountable set, or to show that 0, 1 is not uncountable, And the idea is to start with some sequence I will call x1, satisfying some property. Then we extract from this one, so x1 is, then from x1, maybe I need to use the whole board. So we start with the sequence x, equal x1, we'll say, or x0. Then we construct from it the subsequence x1, and then we construct again the subsequence x2, etc. So maybe here x1, 0, 1, x0, 2, x0, 3, and here it's x1, 1, x1, 2, etc. At the case stage, if we take xk, you have xk1, xk2, and each column is a subsequence of the previous one. And then if we assume, for example, then that the first sequence satisfying some property P1, and this property is kept by taking a subsequence, then when we extract a second sequence satisfying a second property P2, then as the second sequence is the subsequence of the previous, so the sequence satisfies both P1 and P2. And at the stage K, this sequence satisfies property P1, P2, Pk. And if we look for a sequence that satisfies all the properties, the idea is to take the diagonal sequence. So the diagonal sequence, say x21, x22. So the diagonal sequence should be x11, x22. So take the first term of the first sequence, the second term of the second sequence, etc. Now, if we look at this sequence now, it belongs, all the terms belong to this sequence. So it is a diagonal sequence xnn is a subsequence of x1. So it satisfies property P1. But for the second sequence, we can forget about the first element. And starting from x to 2, this is the subsequence of x2. And then it satisfies property P2, etc. So if we're starting by xk, this sequence is a subsequence of xk, and the whole sequence is called eventually subsequence because it becomes a subsequence of xk after some time. We observe that this idea is used in argument to solve many problems in mathematics. But there is no statement. Every time people take a sequence and take a subsequence, etc. So the first thing I will do here that I want to give a statement as a theorem. Just a formulation of this idea that can be used. So the statement is the following. Let x equal xn be a sequence in any space. I forgot to make maybe here. A sequence in some space x. And let Pn be a set or a sequence of properties. And we assume two conditions. We assume two conditions. The first condition that property Pn is preserved under taking subsequent, like eventual subsequent. This means that if a sequence yn satisfies, if a sequence yk satisfies property Pn, and zk is an eventual subsequence of yn of yk, then zk satisfies this property. Second assumption that for every n and for every n, every subsequence of our initial sequence of xn, xk, I will say, has a further subsequence. So I can, every subsequence yn, yk of xn has a further subsequence zk of x, has a further subsequence zk satisfying property Pn. If we fix a property and we fix a subsequence of our initial sequence, then we can find another subsequence so that satisfies this fixed property. Under these two conditions, then xn has, I will say xk has a subsequence satisfying all property Pn. This is the statement, and we can use this statement instead of repeating the method. The kind of properties that can be used is in general related to convergence, but not only convergence. For example, we can use this property. So just an example of property. The following. So for a fixed R positive, I will say that Xn is contained in a ball with radius R. So if we use this property, we can give some short proof of the characterization of compactness by bounded boldness. Total order and compact space for metric case is compact. But we can deal with many with other kinds of properties that are preserved under taking eventual subsequence, not only the convergence. Okay, this is the first part. That to give
this property is not stable under eventual subsequences.
Under
eventual subsequences.
Okay, contain
up to finitely many.
Right? Has a tail. Has a tail. Contained in a. Okay. Okay, thank you. Okay, now for the second part, this is just a statement. So if we want to generalize this argument, this diagonal argument, we need a statement for sequence. And now our goal is to prove a similar result for nets. So the idea, if we start with a net here, then we can having a property, and we have a list of properties. And these properties are kept by taking subnets or eventual subnets. Then we can extract a first subnet, then a second, then a third. But there is a problem here when we want to take the diagonal, because nets are indexed by different subsets. Okay, so first I give the statement, so it's very similar. Let X alpha be a net, and Pn, here there is no problem. The index is different, so be a set of properties and we assume two conditions. The first condition that I will take the first condition that each property is preserved under taking eventual subnets. The second assumption, for every n, for each n, every subnet y beta of X alpha has the subnet Z gamma satisfying property P. Under this condition, we have the same conclusion. Then X alpha has a subnet satisfying all properties P. Okay, we give a constant here. The subsequence is XNN, and our goal is to we try to do.
Can you scroll this down? Thank you.
Okay. Pass to the proof. The proof is similar to the proof for sequence. So let X be X alpha, our initial net. Then we can extract a subnet. So this will be annexed by set A. So if we use our second assumption for P1, so there exists a subnet X1 equal to X1 alpha. Alpha belongs to A1, such that satisfying with property P. Property P1. Here we can write, so there exists some cofinal map P1 from A1 to A, such that X1 alpha is X pi 1 of alpha. Now, as for sequences, we can extract a subnet X2 equal X2 alpha. Now alpha belongs to another subset, another set, satisfying property P2. And of course, we have at stage K, there exists a subnet Xk equal to X alpha K, and alpha belongs to Ak. And here, satisfying property Pk. And here we need some cofinal map Pk from Ak to Ak minus 1, such that Xk alpha equal to X phi k minus 1, k minus 1 of alpha.
No, phi k.
Phi k. Okay, this is the idea for sequences. Now the difference. There is a sequence of sets Ak, and we need to construct our diagonal net. What is our diagonal net?
The phi's, right?
Yeah.
You have to use the phi k's to define it.
Yes. First, I will give the set of index, and then I define the net, and I show that this net is a subnet of our initial net, and an eventual subnet of every xk. So let B equal to all elements like this, alpha 0, alpha 1, alpha n, such that n is an integer. And we assume that alpha I belongs to AI for every I, and alpha I minus 1 is phi I of alpha I for I between 1 and n. Now we define a preorder here. We will say that beta equal to beta 0, beta p, less or equal than gamma equal to gamma 0, gamma q, if we have two conditions that p is less or equal than q, and for e between 0 and p, gamma I, beta I, is less or equal than gamma. I will show that it is clear that this is transitive and reflexive. I will show that it is directed. So now I will show first it is directed, and then I will define my net, my diagonal net. So if I take beta and gamma in B like this, I can take alpha and beta. So alpha is equal to alpha 0, alpha 1, alpha p, and beta is equal to beta 0, beta 1, beta q. I can assume that E is less or equal than Q. So I can choose we can choose alpha p minus 1, alpha q arbitrary in so which I choose alpha e in a I for I onto e plus 1 and q arbitrary. And then I want to find some gamma, which is.
What do you mean arbitrary? They are given already.
No.
You pick any.
For alpha.
Okay.
I pick any element just to have the same length.
Mm-hmm.
Okay, I can continue here. Now I will use the fact that every set is directed. Okay, so I can choose theta, let theta 0 in A such that theta 0 more or equal than alpha 0 and beta 0. This is possible because A is directed. Then let theta 1 in A1 such that if theta is more or equal than theta 1, then P1 of theta is more or equal than theta 0. This is possible because phi 1 is cofine. Now it is possible we can.
Sorry, Youssef.
Yes.
Can you move down the blackboard? Because the other one.
Which one?
The one with the statements, with the proof.
This?
Because, yes, we cannot see. Yes.
Okay.
With the definition of B.
Okay. We can choose now theta 1 more or equal than alpha 1 and beta 1. We will take any one more or equal than this first theta 1, but which is more or equal than alpha 1 and beta 1 because it's directed. And we continue. So we continue to choose for every. So we can then construct beta k in AK for k between 0 and 1 and q, such that theta k is more or equal than alpha k and beta k, and this is first thing. And if theta is more or equal than theta k, then pk of theta is more or equal than theta k minus 1, like we did here. Finally, let gamma q any element, so in a q, such that gamma q is more or equal than theta q. We can take theta q. And then we define theta gamma I for I between 0 and q minus 1, satisfying this condition that gamma I is pi I plus 1 of gamma I plus 1. So we define inductively this gamma. And we are sure, given this condition, that every gamma I is more or equal than both alpha I and beta I. And also we have this condition. So gamma has length q plus 1, and it is more or equal than. So,
but it seems that you're defining gamma I after you know what is gamma I plus 1?
Yes, I knew what is gamma q. Then I define gamma q minus 1.
Okay.
And I continue. So this gamma, it is clear that this gamma is more or equal than alpha and beta. Because for the length, it's gamma, it starts from 0 to q, and it satisfies this condition, so it is in B. Moreover, it is more or equal than alpha and beta. So, yeah. Okay. Now we define the net. So for beta, for alpha equal alpha 0, alpha n in B, we define our net y alpha equal to, maybe alpha is used for the initial sequence. I will say beta. So y beta is equal to x n beta n, but this is x n minus 1 by n of beta n, which is equal to x minus n minus 1 of but this is exactly beta n minus 1, and we can show that this is exactly x beta 0. This is our net. And now I will check that this net is a subnet of my initial net and an eventual subnet of every xk. And if I show this, you get the result. So it's still to check two things. First, I will show that y beta is a subnet of the initial net x alpha. And the second thing, I have to prove that y beta is an eventual subnet of xn for each n. So this allows to prove that this net satisfies property Pn for every n. Okay. Observe that y beta, in fact, is x beta 0. And then we need just to show that the map G from B to A, such that for every beta equal to beta 0, beta 1, beta n gives beta 0 is cofinal. What does mean cofinal? Mean that if we fix some element here, so let alpha 0 in A, then I should find some element in B such that and if I take beta 0 equal to this, beta 0, alpha 0, just alpha 0, it's in B. Then for beta equal to beta 0, beta 1, beta n in B such that beta is more or equal than beta 0. Beta more or equal than beta 0 means that Q is more or equal than 0. It's okay, and beta 0 is more or equal than alpha 0. We have, by definition of the order, beta 0 more or equal than alpha 0. And we are done. So make it. For the second, it is quite easy, yeah? So if we define the set B correctly and the net YB, Y beta correctly, everything is not difficult to check. For the second point, we fix n, and we have to show that our net is an eventual subnet of xn. So let us fix. Eventual means that we need some cofinal map. I will call the psi n from a tail of the from a subset of a n, or I will say delta in a n, such that delta is more or equal for some delta 0 to A. I need to define some cofinal map such that x y beta is no, sorry. We need something in here. We need an, and we need something beta in D such that beta more equals some beta 0, such that y beta is xn psi n of beta. That's what we need. Okay, so we need to give some element here. So let beta n 0 an element in an, and beta 0 equal to beta 0, beta 1, beta n 0 in B. This is possible. If we choose the first element, then we know what is this. This is phi n of beta n 0, etc. So if we choose this element, we have only one possibility. Now, what is psi n? Now I will define psi n. Sorry, I didn't calculate it correctly. Let now psi n from this set beta in B such that beta is more or equal than beta 0 to an. If we have some beta here, I will write gamma to use beta here. If I take beta, if beta is more or equal than beta 0, we know that beta is like this: beta 1, beta 2, beta q, and we are sure that q is more or equal than n because we have this condition. And so we can take beta n. There is a beta n here. So I will show that this map is cofinal, and by definition of y beta, we have y beta is, I write it here, I think, or both here. Y beta is, you start by the last one, but it's equal to the next. So y beta, we know that by definition y beta is equal to xq beta q, but it is also equal to xn beta n. And beta n is nothing other than psi n of beta. This is by our definition of y beta. The only thing we need to show now that psi n is cofinal. And this is just which it is not difficult. I will check it. We need only now to prove that psi n is cofinal. So if we fix some element in AN, let I don't know, theta n 0 in AN, then we have and we put theta equal to theta 0, theta 1, theta n 0 in B. As I told before, there is one possibility, because if we fix the first one, the last one, the other are necessarily defined in a unique one way. Then now, if for beta we can choose beta 0 more or equal than this theta 0, or theta 0. And of course, there is beta 0, so I will take another notation. Let theta 0 more or equal than theta 0 and more or equal than beta 0. This is possible because B is cofinite. And if we write now if delta equal to delta 0, delta 1, delta Q is more or equal than delta 0, then delta is more or equal than beta 0. And then the component delta n equal to psi n of delta is more or equal than this fixed element. And this shows that our map is cofinite and everything are well. Okay, this completes the proof, because now our net is a subnet of the initial net and is an eventual subnet of every net xn, so it satisfies property Pn. Okay. So here the construction is, the beginning is like the case for sequences, but for nets we need to be careful about the index set. Okay, our third, in our program we have 4 things. The first is very short, so just I gave the statement as a theorem for the diagonal process. I prove a countable version for nets, and this countable version is somehow constructive, so we can construct this diagonal net. Now the general case. Now our assumption are the following. Let X alpha be a net in subspace X, and I belongs to deep I, a set family of properties. And we have the same conditions. We assume two conditions. The first one, that each property is preserved under taking eventual subnets, and each net, and for each n, for each I, every subnet of X alpha, I will call it Y alpha, Y beta, as a subnet, every subnet Y beta of X alpha has a subnet Z gamma satisfying property Ti. Then the same conclusion, there exists a subnet of the original net. Net X alpha has a subnet satisfying all properties.
And there's no condition on the cardinality
No condition.
of I or big I.
No condition. For the proof, in the proof, we will use the lemma of Zork. So we need some notation. So let J be the set of subsets, non-empty subsets of I, and F and H be the set of pairs. I'll take F and XF. Such F is a subset of I, and XF is a subnet of our net X, satisfying, satisfying property pair I for every I in F. Of course, H is not empty. We can just take F consisting of one element, and by our second assumption, we know that there exists some subnet H empty, and we will show that H is no, we define for an order. So for Fxf Jxj, we write we define an order here. We say that Fxf in order to not repeat, I will just write this is less strictly than if F is contained strictly in J, and Xj is an eventual subnet of Xn. So we obtain here an order, as it is very easy to show that if we take an eventual subnet of an eventual subnet, it's also an eventual subnet of the first one. So this, we get an ordered set. Which is not empty. And we will prove that the condition of Zorn's lemma is satisfied to get a maximal element, and then show that this maximal element should be of the form I xi. But okay, but it is not easy to prove that. The difficulty here lies in the additivity condition. Okay, so let's start by taking a shell. This one.
No, the first one. The one.
This.
No, this one. I mean, this.
This also.
Yes.
Okay, you need the definition.
Well, it is written there so that we can see.
Okay. Now we will show that we have the additivity condition. So let H prime equal to F xf when F belongs to some subsets. Be a check in H, and that is totally ordered. So F also is totally ordered as a subset of J. And now we want to show that there is an upper bound, H prime. Okay, we define a new set. Of course, if there is a maximum element, we are done. So we assume that F has no maximum element. And we define, let delta be the set of all delta equal to alpha F pairs alpha F belongs to F and J, such that alpha F belongs to F for every F, and J is an element of F, fixed F. Now we will, this delta will be the index set of some subnet of X, and this subnet together with a set of properties that satisfies will be an upper bound. So first we will we'll put a preorder here and show that delta is directed, and then define our net. So we write delta equal alpha F in F J less or equal than delta prime equal to alpha prime F J prime if natural order here, that alpha F is less or equal than alpha prime F for every F, and J is contained in J prime. Now, this is clearly reflexive and transitive, and we want to show that it is directed. So if we take two elements, so our purpose now to show that.
Sorry, I'm confused. But alpha F is in F.
Yes. Sorry. Alpha F is in. Okay, F is in F. Thank you. Alpha F is in gamma F. What is gamma F? We say that XF is a subnet of X. So there is a cofinal map phi F from gamma F to the initial A. For alpha, we have phi alpha of alpha, such that XF alpha is equal to X phi F of alpha. So thank you. So, what is that? It's the only place. Okay.
Youssef,
Yes.
we need to make a break at some point.
Now, well, we can take now.
You're the boss.
Okay. Before starting to prove, okay. Take a break. Okay. Okay, maybe this is the hard step in the proof, and I need to be more slower. So I want to show that the condition of Zorn's lemma is satisfied. So I take a chain and I want to show that there is an upper bound. So if this is a chain, then if you take another element, if you take f x f and j x j, two different elements here, then one should be more or equal than the other. For example, we have this. And this means that f is contained strictly in j, and xj is an eventual subnet of its f. Okay, now this means that, remember that xf is a subnet of x. So in some stage we need to use the fact that xf is like that, xf alpha belongs to gamma f, and we have some cofinal map from gamma f to A. Also, I will translate this. This means that there is some alpha jf0 belongs to gamma j, and a cofinal map phi jf from the set of all alpha in gamma j, such that alpha more or equal than alpha 0 jf to gamma f cofinal, such that if I call this gamma j f, such that for alpha in gamma jf, x j alpha is x f phi jf of alpha. Okay. Now I can start our proof of adjective property. we can start by a simple case. But of course, if xf or xk, sorry, if kxk is more or equal than fxf for every f in f, we are done. And so if not, it will work. What will be the k and which will be the net? We need some upper bound. We will find an upper bound, say h x h. No, h is not allowed. No, I will take L x L, and L will be the union of element f. F belongs to f. It's a natural candidate. But what is the difficulty is to find this one. So for this one, I will start by giving the index set and then define the net. So let delta equal to all element like this, the pair alpha f, f in big F and j, such that alpha f belongs to gamma f for every f, and j is any element in f. I take this set. And I define a preorder. I will write delta equal to alpha f j less or equal than delta prime equal to alpha prime f j prime if alpha f and alpha prime f are in gamma f. So I assume that alpha f is less or equal than alpha prime f for every f, and j is contained in j prime. It's a very natural order here. And just the reflexivity and transitivity are very clear, then we will show that it's directed. So we will show that it's directed. For example, I will take two elements. Also directed is not difficult. It follows immediately from the fact that gamma f is directed and the fact that the family f is totally odd. If you take delta equal alpha f j, delta prime equal alpha prime f j prime in delta, we can choose for every f, we choose alpha second f more or equal than alpha f and alpha prime f. This is possible because gamma f is directed, and j second is the maximum of j prime. You know that j is contained in j prime or the converse. So delta second equal to alpha second f j second is more or equal than delta and delta prime. So it's directed. Now I will define the net. I will call it y. So we define the net y by y delta equal to or delta equal to xj alpha j, or delta equal to alpha f. And I will show, like for the previous proof, I will show two things. That this net is a subnet of every x alpha, an eventual subnet of every x alpha, and is a subnet of the initial net. Can use this part?
Yes, yes.
So first thing, we show that y is a subnet of x. The map is clear here. What is the map? I will take phi from delta to A to delta equal to alpha f j. We take x j alpha j, but alpha j is what? Alpha x j alpha j is by definition no, sorry, it's phi j of alpha j. Remember here, there, no. Yes. Okay, here. Phi j from gamma j to A. So this is an element of A. And now you have.
Sorry, where is alpha f? Alpha f lies where? In GF. Alpha f g lies in GF for every f, right?
Yes, alpha j is here. Because j is here, I can recall that f is any element of f and j is a fixed element. So we have some alpha j here.
Yes.
So now I will show that this, if we take y.
This is cofinal.
Yes, if you take y delta, it's by definition, it's xj alpha j xx phi j of alpha j xx phi of delta. And just we want to show that phi is cofinal. So we need to show that phi is cofinal. What do you need here? To fix some, so let alpha 0 in A be fixed. Then Okay. Now I will use the fact that this is cofinal. Then for every
G.
but I need all of them. For every f in f, for every f in f, there is this alpha 0 f in gamma f, such that if alpha is more or equal than alpha 0 f, phi f or alpha is more or equal than this alpha 0.
Mhm.
And what I take now, J is fixed, so we take let delta 0 equal to alpha 0 f, f belongs to f, and J. And we will check that for delta more or equal than alpha 0. So for, I think I need some other detail. So that, yes, I need other details, but I can try to prove this one. It does not work. So for delta more or equal than delta 0, now delta equal to what? Delta equal to alpha f, f in f and h. More or equal than delta 0 means that alpha f is more or equal than alpha 0 f, and h is more or equal than j is contained in these are subsets. J is contained in H. Now, if I compute what I need, I compute phi of delta. Phi of delta is what? Phi of delta is
It's hidden.
it's
hidden. We cannot see the definition.
It's alpha H. No, phi of delta is given.
Oh, it's there.
Yeah.
Yes.
Phi of delta is alpha. This one. It's alpha H.
No, it's phi. It's phi h.
Yes, it's phi H of alpha H. I need to show that this is more or equal than alpha 0. I think it works because, yeah, it works. The more tricky things will be needed in the second step.
Why is this bigger than alpha 0?
Because alpha H is more or equal, alpha H is more or equal than alpha 0
alpha
H.
0 h. Yes.
I say that it will not work, but here it's okay, it's fine. In the next step, we need some more care. Okay, now, so in this part, we show that, in fact, it's a cofinal, and so our net y is a subnet of x. So the next step, the final step to prove, no, not almost, the last one, we need now to show that y is an eventual subnet of what time is it? Watch.
25.
We will show that y is an eventual subnet of x f or x j for every for j in f. Okay, recall that. So we need a cofinal map going from, we need some map. I will call it psi j. Maybe j is not. I will anyway. Psi k from a subset of delta. Delta in delta such that delta is more or equal than delta 0. And this delta 0 should be fixed to gamma k, such that for each delta we will take alpha k. Because that delta is like this, delta alpha f j or f right, j. And we should to choose this delta 0. Okay, so how to choose delta 0? So delta 0 is like this. So we have to choose this element and this element. So delta 0 would be something like that. And it will be k. But what is this one? With alpha f0 is more or equal than alpha 0 for k contained in f. Alpha k, alpha f k, k contained in, we should compare k and j. Okay, f. Right.
No, what is G there?
K. This for f containing k. And there is arbitrary, so alpha 0f arbitrary. Okay, for the otherwise, for the other case. So we will show that this works. What we need to show? We need to show that this map is okay. So here, if you take J, so you need to take E. If you take this element here, so you are sure that this J is more or equal than contains K. And then we can define phi K J of alpha
KJ.
J. Right? Because here, if we take this element in this set, then it is delta is more or equal than delta 0. And then this J contains K. And we have this. Also, the index, the alpha J, should be more or equal than this. So we know that alpha J is an eventual subnet of alpha K, and it starts from this element. So it is not difficult to show that Pk is final, and you see that y delta here is y delta is what by definition is xj alpha j, and this is by definition x. Now alpha j is more or equal than this one, so this is phi. The figure is a j k of alpha j. Okay. Okay. And this is exactly xk psi what psi k of delta. Of course, we need to show that it's cofinal, but the proof is very similar to that the proofs before. So the next step is to show that if we have now, if you take k is equal to all the union of f, and we take xk is equal to y, then we show that y is a subnet of x, is an eventual subnet of every one. So this net satisfies all properties here, because xk is an eventual subnet of xf for every f in f. And so it satisfies all property pi when I belongs to f. And then xk satisfies all properties pi when I belongs to h, to k. So this means that this is an element. If you take now kxk, this belongs to our family H and is an upper bound. Now we will show that this upper bound should be, this element should be R. Otherwise, yes.
The maximum.
The maximum, yeah.
Not the upper bound.
Okay, okay. So the next step, let LXL be a maximal element in H. And we need to show that L is equal to R. So otherwise, there is an extra point, and we apply condition 2 for this extra point to have another subnet satisfying all this property, but also the property I, and we get an element which is strictly larger than this one, which is a contradiction. So we show that I can ignore the thing here. It's the same idea when we present another proof of Tikhonov theorem. for the partial cluster point. If the maximal element is not the whole set, so we can add another point and extract another subnet. I'd like to mention some applications and
Uh, 25 minutes.
25.
Yes.
I suggest that this principle could be used as a tool which in some cases replaces Tikhonov theorem. So we don't need to construct, to define some compact, etc. So as an example, we can, as an example of applications, we can give a very clear, neat proofs for many classical results in function analysis. For example, the Tikhonov theorem itself. For the Tikhonov, for the metric case, we can prove that if we have a product of countable metric case, metric compact space is compact. And in this case, we can use the classical diagonal process. But if we have a countable product of topological space, we cannot do it with the first diagonal process. So we use our second, our countable statement for the diagonal process. So for everything using separability, we can just use the first one, because the first one is constructed. We can construct this diagonal net. However, in general case, just we prove the existence. But for Tikhonov theorem here, if we have a product and our property will be pi, we will say that a net satisfying the property pi if the component, if we take x alpha, so x alpha satisfying pi, it means that x alpha of I converges. And if we start with a net here, we can see that for every subnet and for every property, if we use the fact that xi is compact, the condition is trivially satisfied. And all these properties are preserved under taking subnets. So we have a subnet that satisfies all these properties and it converges. So this is another short proof of Tikhonov theorem. But it can give a proof of other type of Tikhonov theorem. Assume that we have a convergence, but which is not topological convergence. We can assume that X is a vector, a subset of vector lattice, for example. And we assume that Xi is order compact, which means that every net has an order conversion subnet. Then the product is also order compact. So this type of Tikhonov theorem, we don't need the topology here. So for every kind of convergence, we can show that a product of compact space is compact. And the classical application of Tikhonov theorem is Banach-Alaoglu theorem. that states that if we take Banach space X, then the unit ball in the dual is weak star compact. To prove this using Tikhonov theorem, we need to define some spaces and say that this is a compact, etc. However, if we use our theorem, we need to define property. What is property are easy here. For every x in X, what is Px? That X alpha star of X converge. This is the property Px for X in X. And clearly, the property is preserved under taking subnets. And clearly, if we take a fixed X and we start with a net here, so this net is bounded, so this real net has a subnet, it's bounded, so we are in R. So it has a convergent subnet. So to check that the conditions of the theorem are satisfied is easier than check that Tikhonov theorem can be applied. Because for Tikhonov theorem, we need to define some spaces and identifying, etc. But here, it's easier. And then we deduce that this net has a subnet that converge pointwise. But the pointwise limit is linear and with norm less or equal than 1. These are trivial things. So even it is not a very strong application, but the idea that I want to present here, that this theorem of diagonal process is easier in application than Tikhonov theorem. First, it can be applied in other contexts, not topological. But even in topological context, it is easier to be applied. Also, we can give a natural proof of Arzela-Ascoli theorem. If we take K, a compact space, and we take a subset H in C of K, which is equicontinuous and bounded, we can take it closed to be compact or to be relatively compact. So we can apply this argument easily to show that with a natural way. So we start with a net. Even here we work with a sequence, but it's the same. Start with a net, and for every point we have a convergence. So we have a pointwise limit, and after that it is not difficult to show that the pointwise limit is a uniform limit and it is also continuous. We can also give a proof of Schroeder theorem in any step. We don't need to. So here we use Tikhonov theorem. In Schroeder theorem, we use Ascoli-Arzela theorem. But we can use directly the diagonal process and we get more direct proof. Schroeder theorem, I mean that if T is compact, then the adjoint is compact. And we can give, and the application is also true. And also we can give a proof for the application without using the T double star with the same idea. So there is two kinds of application. One, to simplify or to get shorter proofs for known things. But there is other application that to prove open question, like the following. I mentioned in the beginning, if we take let E be a Banach space and X be a Banach lattice. If Tn belongs to L of Ex is linear and bounded, such that Tn converge to T in the usual sense, and Tn is UN compact. I will take a UN compact for each n. Then T is UN compact. This is an open question left of since 8 years. So this is solved for the case of sequentially UN compactness case, because we can use it as standard diagonal argument. And in the proof is very similar, but just when we apply our second theorem, we can get a net satisfying all properties. What are properties here? Pn here are, we say that X alpha satisfies this phi satisfies Pn if Tn of X alpha has a UN conversion is UN conversion. Okay, this means that for some y we have this Tn X alpha minus y, and for u converge to 0. Every positive u in for every u in X class. Have I the time to prove this, or
We have 15 minutes.
15? Okay. Maybe I give the sketch of the proof and I speak about other applications. So for the proof, we start with a norm bounded net. X alpha in E. And we need to find a subnet such that subnet y beta. So we have to show the existence of a subnet y beta such that T y beta converge UN to some y, to some z, say. Okay, so we have this a net, and we need to apply our theorem. So this is the property Pn. So as Tn is UN compact, every subnet of X alpha is norm bounded, and so it has a subnet such that the image by Tn is UN convergent. And clearly properties Pn are reserved under taking eventual subnet. So by diagonal process. There exists a net y beta such that Tn of y beta converge to Zn un for every n. So we will show two things, that Zn is a net in X. So we will show that Zn converges in norm to Z, and that we will show that Tzn, y beta converge un to Z. Please tell me if I have just 5 minutes. Okay, for I, we will show that Zn is Cauchy. So we will write Zn or Zp minus Zq by using triangle inequality. So it's Zp minus Tp x beta plus Tp x beta minus Tq x y beta, sorry, plus Tq y beta minus yq minus zq. Okay, and this is less or equal than Zp minus Tp y beta here we will Zp minus Zq after mu. We need to use that. We need to use that Tp y beta converge un too. So, and this is the last one. Tq y beta minus Zq from mu. Okay. So this is less or equal than now we can choose, because here there is no beta, so we can choose beta such that this is, we know that Tp y beta minus, or if you want, we can compute the limit over beta. This does not depend on beta, so Zp minus Zq of alpha mu. And if we take the limit over beta, this converges to 0, and this converges to 0. So this less or equal than this quantity, but this quantity is less or equal than, we can ignore the u, and this less or equal than Tp minus Tq. But this happens for every u. So when we take the supremum of u, we get we can take u equal to Zp minus Zq. So we have this equality, and this shows that the sequence Zn is a Cauchy sequence, so it converges. Okay, so I will ignore the last part, but it is not difficult. Okay. Before I mentioned something related to yesterday, I give a connection between the two types of order convergence, and I mentioned that if we take a set A in a X, which is a vector lattice, then if we compute the order closure, we get the same if we work with two types of order convergence. And I said that it is also the same if we consider the unbounded order. And to show that the reason here relies on the fact that if we have a net that converges in this sense, we have a subnet that converges in this sense. And we have a similar result here. Yeah. We have a similar result that we can obtain using the result concerning the order combined with the diagonal process. So this is the result.
You take
So the theorem, if X alpha converge U O to X, then X Y beta converge U O1 to X or some subnet. And here, what are the property for every U, for U positive? The property Pu is the following, but Z gamma minus X and from U converge to 0 or 1. So if we take the net X alpha, it is clear that this property is preserved if we take an eventual subnet. And then if we take a net here and we take a subnet, this subnet, if we fix U, then we will have a subnet of X, inside X beta minus X and phi. This converge in order to 0. And by the result obtained for order convergence, there is a subnet that converge to 0 or 1. So the second condition is satisfied. And then the conditions of our theorem are satisfied, and we have this for every U. So there is a subnet that satisfying this condition for every U. So this implies that the subnet converge in this sense. As I mentioned before, this can apply also for Lebesgue property, and we can show that Lebesgue property does not depend on on the type of order convergence. Okay, now can stop here. Thank you.
Okay.